This is the lecture for Part 2 of Section 7.1, Definition and Examples of Groups. Now, a ring has two operations, the ring addition and the ring multiplication, whereas a group only has one operation. And so one thing we can investigate is, starting with a ring, can we obtain a group out of it? And we can obtain a group from a ring by restricting our attention to only one of the two operations. And first we'll investigate the ring addition. So theorem 7.1 tells us that every ring is an abelian group under the ring addition. To prove this, suppose R is an arbitrary ring. And if we look at the first five ring axioms for the ring addition, they correspond exactly to the 5 axioms for an abelian group. R1 is closure under addition, R2 is the associative law of addition, R4 is the existence of an additive identity, R5 is existence of additive inverses. These correspond to G1, G2, G3, and G4, and R3 is the commutative law of addition. That corresponds to our axiom for an abelian group under the ring addition, with identity element 0 sub r, the additive identity in the ring, and the inverse of an element A in R being the additive inverse minus A. Now, theorem 7.1 implies that each of the following rings is an abelian group under the addition. The set of integers z, the set of integers mod n, z sub n, the rational numbers, the real numbers, the complex numbers, and matrix rings such as M of R, those are the matrices with real entries, or M of z sub 2, those would be matrices with entries from z2, and polynomial rings such as z bracket x, r bracket x, and z sub n bracket of x. Now note that a non-zero ring R is not a group under the multiplication. In the case that R does not have a multiplicative identity, then R does not satisfy axiom G3, existence of an identity. In the case that R does have a multiplicative identity, then 0 sub r, the additive identity, does not have a multiplicative inverse, so R does not satisfy axiom G4. So either way, the ring R will not be a group under the multiplication. Now, if we restrict attention to just the elements of a ring that do have multiplicative inverses, then we do obtain a group under the ring multiplication. And this is the result of theorem 7.3. For all rings R, if R is a ring with identity, then the set U of all units in R is a group under multiplication. To prove this, suppose R is an arbitrary ring with identity, and suppose U is the set of units in R. Remember now, the units are the elements in R that have multiplicative inverses. We need to verify the 4 group axioms for the set U. So first is closure. For all A, B, and U, A times B is in U. So if we suppose that A and B and U are arbitrary, we need to show that A times B is in U. To show this, we need to show that AB is a unit. That is, AB has a multiplicative inverse. Now, since A and B are both in U, then A and B both have multiplicative inverses, A inverse and B inverse. And we want to show that AB inverse is equal to B inverse, A inverse. And to show this, we have to show that if we multiply B inverse A inverse times AB on either side, we obtain the identity. Well, AB times B inverse A inverse, using the associative law of multiplication, will be A times the quantity B inverse A inverse, which is A times the multiplicative identity 1 sub r times A inverse, which is just A times A inverse, which is 1 sub r. And then in the other order, we have B inverse A inverse times AB is B inverse times the quantity A inverse A times B, which is B inverse times 1 sub r times B, which is just B inverse B, which is 1 sub r. And that tells us that B inverse A inverse is a multiplicative inverse for AB, and therefore AB is a unit and U satisfies G1. For G2, we have the associative law. For all A, B, C in U, A times the quantity BC is equal to the quantity AB times C. Now, by ring axiom R6, the associative law of multiplication holds for all elements in R, so holds for elements of U. So axiom G2 holds. Next is G3, the existence of an identity element. there exists an element E in U such that for all A in U, A times E is A, and E times A is A. By assumption, R has a multiplicative identity 1 sub R, which satisfies the conditions to be an identity element. We just need to verify that 1 sub R actually belongs to U. And since 1 sub R is its own inverse, then 1 sub R is a unit. So 1 sub R belongs to U, and U satisfies G3. Finally, we have G4, existence of inverse elements. For each A in U, there exists an element A inverse in U such that A times A inverse is 1 sub R, the identity, and A inverse times A is equal to 1 sub R. Suppose A in U is arbitrary, then A is a unit, so by definition has a multiplicative inverse, A inverse. We just need to verify that A inverse belongs to U. Now the two equalities, A times A inverse equal 1 sub R, and A inverse A equals 1 sub R, imply that A satisfies the conditions to be a multiplicative inverse for A inverse. So A inverse inverse is equal to A. Therefore, A inverse is a unit, so A inverse belongs to U, and thus U satisfies G4. And therefore, U satisfies the 4 group axiom, so is a group. Now, in a field, all non-zero elements are units. So the next theorem follows immediately from theorem 7.3. This is theorem 7.2. For all fields F, the non-zero elements of F, which will denote F star, form an abelian group under the field multiplication. So theorem 7.2 implies that the following sets are abelian groups under multiplication: the non-zero rational numbers Q star, the non-zero real numbers R star, the non-zero complex numbers C star. As another example, for any prime P, Z sub P is a field, so Z sub P star, the non-zero elements in Z sub P, is a group under multiplication mod P. And for an example, denote the multiplicative group of units in Z sub n by U sub n. By theorem 7.3, U sub n is a group under multiplication mod n. And according to theorem 2.10, an element A in Z sub n, the congruence class of A in Z sub n, is a unit if and only if A and n are relatively prime. Therefore, for instance, U sub 8 will be the elements in Z sub 8 that are relatively prime to 8. So these will be 1, 3, 5, and 7. Now the group of units in the ring M of R of all 2 by 2 matrices with real entries is a group under matrix multiplication. And this group is called the general linear group of degree 2 and is denoted by the notation GL2R. In general, you can look at any size matrix, and so you would have the general linear group of degree n, and that would be denoted GLNR. Now, since a matrix is invertible if and only if its determinant is non-zero, then we can write out the set GL2R. This will be the set of 2 by 2 matrices A, B, C, D, where A, B, C, and D are real numbers, and the determinant AD minus BC is not equal to 0. Now the set of positive rational numbers, which we'll denote with a double star, Q star star, and the set of positive real numbers, R star star, both form abelian groups under multiplication. To prove this, first note that the set of positive rational numbers forms a group under multiplication because the product of 2 positive rational numbers is positive. The identity element, 1, is positive, and the inverse of a positive rational number is positive. So that will tell us that the 4 group axioms hold for the set Q star star. And similar statements hold for the set of positive real numbers. So both of these are abelian groups under multiplication. Now, starting from old groups, we can construct new groups by looking at the Cartesian product. So the operation in the Cartesian product will be defined by applying the individual group's operations component-wise. And this is the result of theorem 7.4. So let G be a group with operation star and H be a group with operation diamond. And we can define an operation square on the Cartesian product G times H by An ordered pair GH square an ordered pair G prime H prime will be the ordered pair G star G prime H diamond H prime. This is for all ordered pairs GH, G prime H prime in the Cartesian product. Then G times H is a group under this new operation square, and if G and H are abelian, so is G times H. And if G and H are finite, then so is G times H, and the order of G times H will be the product of the orders of G and H. And the proof of this theorem is left as an exercise. As an application of the theorem, we can consider an example. If we let Z sub 2 equal 0, 1 be the group with mod 2 addition, and let U8 be 1, 3, 5, and 7 be the group of units with mod 8 multiplication, then Z2 times U8 is a group, okay? And the operation is defined by the ordered pair AR star, the ordered pair BS will be the ordered pair A plus B R times S, with mod 2 addition in the first components and mod 8 addition, multiplication in the second components.